This is the AS Core Pure paper from 2023. Let's just go ahead and do it. So Ki is just K times 1001. It's obviously two-dimensional because these are. So we just need x minus 3z to be K, and we need 9 minus 3y to be 0, and so on. We'll get 4 of these. The one we can make progress on is the first one. We can solve that for y. Sorry, the second one here. We can solve that for y. And then once we've got y, we can go into here and solve for z, which is very helpful. So z is 1, clearly. And then we can go in here with z and y, and we can get k. And then we can finally go over here with k and z and work out x. And that's all the things that we were asked to do. So we're done with that question. If that's a root, then minus 3 minus 4i is also a root, which is the first thing we'll write down. There's a few ways you could do this from here, but I just decided to think about what this looks like in vectorized form, which is z minus this into z minus this into z minus whatever the other root is. But we can focus on the z minus this and this first, because if we expand that out, it turns out not to be too bad, because of course these are both plus 3's really, and then the i's cancel when you add them together. And then when you times them, you just get 3 squared plus 4 squared, so that's going to be that. And then, of course, yeah, like I said, we can say that times some other root z minus alpha is the original thing. And now we can just see here that alpha must be 7, I guess, to make this, or minus 7, I guess, because it needs to make this a plus as well. And then once you've got alpha is minus 7, which makes this whole thing plus 7, you can then just expand this out and work out A and B. There are probably lots of other ways to do that. When we're drawing the diagram here, it looks a bit like this. We'll just call this the imaginary and this the real axis. I don't think you need any more detail than that. I think that's enough. And f of z plus 2 is just a shift of the graph 2 to the left. And so the roots are also going to move 2 to the left. If there was 1 at minus 7, then that means it now is at minus 9. And these ones are now at minus 5 plus and minus 4i. And that's that question done as well. So describe this transformation. You just need to know this. It's a rotation in the x-axis because this one is 1. A y-axis would have 0s and 1s down the middle bit. So this is a rotation around the x-axis, and then you just need to get the degrees from these numbers here. Because you don't get this in the formula book, because this is what I'm thinking about there in my head. I need cos theta to be this, which obviously gives me theta is maybe like 30. But then I just need to quickly verify that it's not like the next one along. And to do that, I'll just check that minus sine theta or minus sine of 30, since that's my candidate rotation, is also equal to minus a half, which it definitely is. That's fine. But yeah, this could have been like theta is, well, what's the next one along that makes root 3 over 2? Like, goes down and then up again, doesn't it? Like 300, I guess, is the next one that gets that far. So then, of course, you check whether the sign matched up with that. So you do have to do some checking there. Anyway, state the error made by the student when they're multiplying. Oh, sorry. So A is followed by B. Well, if A is followed by B, A came first, which means if you're timesing by some coordinate, you should be doing that coordinate A to the left of it and then B to the left of that. So it should be BA, not AB, because the coordinate goes here and you apply A first and then you apply B. So it works like that one, outwards, not inwards like this. So yeah, they're going the way around. To determine the correct matrix C, so we just flip those over. This is a calculator. It's 1 mark question, so just multiply them with a calculator, and you should be good. Question 4 then. So there's probably smarter ways of doing this, but I just realized the denominator, just did some GCSE maths, and you end up with this. That all cancels out really nicely to leave a half, and it's okay. It's obviously a half, and that's fine. And now we have that we're doing this to the power n, but this we know is just this. So we're actually just doing this to the power n. Now, all we need to think about is, what does this complex number look like? Well, it's obviously just over here at a 45-degree angle, because, of course, it's 1 across and 1 up. The half doesn't really matter. So if we're going to apply this complex number a bunch of times, multiplying itself, remember when you multiply complex numbers by each other, the argument just adds. So it's 45 degrees right now, so we just need 4 of them to get it to 180 degrees, in which case it will be back on the real axis. So we just need 4 of them. If you had 8 of them, it would also go back to the real axis and so on, but 4 of them will do. 1, 2, 3, and 4 turns will get you somewhere over here, and that would be good enough. Now the complex number this has this and this, so a nice trick you can play here is that the modulus can act inside of the power 10, so we can just say it's this, and now of course we can take the 10th root of both sides to get this. So now we know that a squared plus b squared is 3 squared, or the root of a plus b squared is 3, I guess you could say, or yeah, sure. Both things there were true. And now we can think about this one here. And again, think about what the argument of z to the 10 does. Every time you times a complex number by itself, the argument doubles. So if you're doing that complex number 10 times, whatever the argument was, you're going to have 10 of them when you're doing this. So this is the same as 10 lots of the argument of z. I'll just repeat that, I guess. Every time you times a complex number by itself, or any other complex number, the arguments add. But if you're timesing a complex number by itself, that means, for example, the argument of z squared is just twice the argument of z because you add z to z, and you extend that logic and you get 10 argument of z. Of course, just divide by 10 and take tan inverse, I guess. Yeah, because z is just, or the argument is this, right? So the argument is just tan inverse of b over a, right? That's how you get the argument from here. So that's this, you get this. That's what tan inverse of this thing is. You can cross multiply and you'll end up here. Now we can just substitute that value for a maybe into here. So a squared is just going to be 3b squared. And then you can solve for b, which will be this when you divide by 4 and then square root. Now b could be plus or minus 3 over 2, except it can't, because we know that the arguments, how do we know which way it is? I can't remember. It's negative. Why is it negative again? Does it tell me? I made these slides a while ago. Is it because, yeah, the argument, sorry, it's right here. The argument is minus pi over 6. So the argument of just the single z is down here somewhere. So that means that the b value is negative and the a value is positive. So b is minus this, and therefore a just times by root 3 is positive that, with the minus as well. So we have this. Good. Question 5 then is just a nice little bit of rotation. So we'll get out, firstly, we'll say that this is 2 because when y is 0, sorry, when x is 0 here, when x is 0, y is clearly 2. So we're going to rotate it around this way. So that's going to be pi, lots of the integral of x squared dy if we're going around this way. X squared is, of course, just 2 minus y, which is very convenient. It's not a difficult integral to do at all. We put the numbers in, which is still not difficult to do. And then we just say density is mass over volume. And we have a density of this, so we're going to do density times volume is mass. We know the volume is this here, so the mass, therefore, two significant figures is just this when you multiply that. Give a limitation in the model, you can write any of these things. I would suggest that given that you know that this question is going to come up in this paper, when you do this paper, just plan to just immediately write one of these things down. Just go in, having memorized one of those 6 or 7 things that are there, and just know you're going to write it. Don't waste time like I am right now. Just write one of those things. It's always going to be the same. And likewise for part C, I thought this was kind of interesting. I would have instinctively said 5,700 is quite close to this, so therefore it's a good model. And I would have got a mark for that. But what's interesting is that you can also say 200 is a large number, so it's not a good model. Like, as long as you just justify what you're saying in some way, you'll get a mark apparently. So that's quite fun. And yeah, let's move on. We got the vectors question here. So L2 is parallel to this. Show they're perpendicular. Well, if they're perpendicular, then their direction vectors dot to make 0. So let's just do this dot this. Be clear with the working because it's a show that question, and therefore perpendicular. The plane contains the line L1. Okay, well, if the plane contains this line, then it also contains this coordinate because this line has this coordinate on it. So the plane must have this coordinate in it and is perpendicular to this. So what we can say is we can write the plane in this form where r, which is just x, y, z, dotted with the perpendicular vector is some value k. But since I know it goes through this point here, I can just put that point in to work out k and just dot those out. You'll get k is 2. And so therefore, and then finally, of course, you can, because r is just x, y, z, you can dot those out to get x plus 2y minus 3z is equal to that 2 that we found before. Verify that this is on the plane. Well, you just put 3, 1, 1 into here, and it checks out, so that's fine. Given that the point of intersection has coordinates 2, 3, 2, and this and that to determine the coordinates of B. So what we'll start by doing is we'll start by defining L2, because we now know that it goes through this coordinate here. So that's what it tells us here, because if it intersects pi at this coordinate, then it must go through that coordinate, plus some amount of its direction vector that we were told earlier. And we can group that up. Well, I'll group it up in a second. I'll also say that the distance between PQR and 2, 3, 2, because that's the point A and B, I believe. No, it's not. A is this one here, sorry. The distance between PQR and 3, 1, 1, which is the distance between A and B, is 2 root 5. So we can say P minus 3 all squared, plus Q minus 1 all squared, plus R minus 1 all squared, just the Pythagoras in 3D. That distance is 2 root 5 all squared. Now we can group this up, as I was saying before. Now we can group this up into 2 plus mu, 3 plus 2 mu, 2 minus 3 mu. And we can say that must be equal to PQR. That's just the point that we're trying to find. But of course, that means I can replace P with this in this equation, Q with this, and R with this, which will just give me an equation in terms of mu, which, although it takes a little while and a bunch of expanding that is really boring, you can eventually do, and you get mu as plus or minus 1. Now, if mu was 1, then you'd have 2 plus 1 times 1 is 3, and you'd have 3 plus 2, and you'd have 2 minus 3, which is minus 1, but it tells us all the coordinates are positive. So u can't be 1, it must be minus 1, and you'll end up with this if you use minus 1 instead, which is good, so it must be this one here. Question 7, shade this, so we're looking for all the points z such that we're closer to 3 than we are to minus 6i, because you need to put that minus in distance from z to minus 6i. So okay, we put 3 there, we put minus 6i there, and then it's just a perpendicular bisector. That drawing, according to the mark scheme, just gets full marks. You don't need to do anything else, or of course shade the region that's closer to 3, I guess. And then determine the exact number for which this is true. So again, let's just get out a picture super quick. So this is the argument to the point 2. So we'll put the point 2 down, is pi over 3. Well, that's somewhere over here, I guess, the half line over there. And this is to the point minus 1. Remember, you still need to do w minus brackets minus 1, just like here, is pi over 6. Well, that's a smaller angle, right? So it's going to come out like this, and they're going to intersect here. How do we find where they intersect? Well, you just pretend this is a normal coordinate geometry progression in the xy plane. So you just find the equation of these two lines, and then find the intersection of them. Now, the equation of these two lines is not too difficult to get, because there's a nice little trick, which is tan theta is the gradient of any line, where theta is the angle to the horizontal. And that's true because if you imagine a theta being written here, tan theta is just opposite over adjacent. If you imagine drawing a little triangle, tan theta, if theta's there, is just opposite over adjacent. But the gradient of this line is also just rise over run, which is those same two measurements in that imaginary triangle. So tan theta is just the gradient. But we know theta is pi over 3. So tan pi over 3 is the gradient of this line. So this is just y minus y1, y1 is 0, equals m tan pi over 3 into x minus x1, which is just 2. Tan pi over 3 is that, so we can just do that and expand it out, and we get this equation. And likewise for the second one, tan pi over 6, because the angle is pi over 6 here. Again, y minus y1 equals mx minus x1. Sort it out, and then find the equation, find the intersection between those two. You can times by root 3, which is very nice. You get x is 7 over 2. Which means you can then substitute that back in, I guess, to either one of these two lines. It doesn't matter which, to work out y is this. And then the complex number, remember this is originally a complex number question, is just 7 over 2 plus 3 root 3 over 2i, because that's just the amount across and the amount up to get to this point here. And we're done with that question too. Use the standard results for these two things to show this. So first we expand this bad boy out, and we get a bunch of different sums. Take all the constants out as well, because now we can apply that this here is just n. This, you also need to know, is just n into n plus 1 over 2. And this one, I'm pretty sure is given in the formula book. And is this, I'm pretty certain that's, in fact, I'm 99% certain that's in the book. So you just apply that, times it all out, and now start factorizing. You can take out, well, look at this. It's taken out a third n. So let's just take out a third n regardless of whether or not we want to. So that leaves a 2 behind here and a 6 over here to get a third times 6 equals to 2. And then a 3 there. And now let's just notice that all of this would just make a quadratic if I simplified it. So let's do that, because I know as long as I simplify it up, I can just factorize quadratics. This one's actually super easy because the n's go away, so you just immediately get what you were being asked to get, and a is 5. And that'll be that done. Hence determine the sum of all positive odd 3-digit integers. So, well, these are obviously odd integers here. 3-digit ones start at 101 and end at 999. So the R value that we need to use to start at 101 is, I think, 51, because 51 times 2 is 102, take away 1 is 101 squared. So that will be the first odd digit squared. And we have to go up to 500, because that makes 999 in here. Now, we can't do this because it doesn't start at 1, so we just break it down into two sums, go from 1 to 500, and then from 1 to 50, and take that bit away, and then we can just apply this formula that we have here in a calculator, and we'll get this big number here to finish. Only 2 questions to go. P is this. Show P is non-singular, so, okay, singular matrices have determinant 0. So we're just going to find the determinant, which is k times this determinant minus 2 times the determinant of these 4 here, plus 7 into this determinant. So I'll just do that, and you get this, which simplifies this, which simplifies to that. And we can check that this is never 0 by just looking at its determinant, which is minus 92. So therefore, this quadratic has no roots, and it's negative, so it's just entirely below the axis. And so there's no values for which this whole thing would be 0, and maybe just write that down. Q represents a linear transformation, sure. Under T, the point A and the point B go to these places, distance is this. So okay, let's just transform A and transform B. So we're going to do this times A, and then this times B as well. So firstly, that's that. It's just 2A minus 2 minus 3A, that's it. And then this one likewise. Now, the distance here is root 58. We've actually kind of just already done this, right? It's just Pythagoras. It's just this minus this all squared plus this minus this all squared, or the other way around. I've done it the other way around. Perfect. Doesn't matter. This minus this all squared plus this minus this all squared equals root 58 squared. You do some really boring algebra, and you end up with this, and you get two answers for A using a quadratic calculator, and you get this, and you ignore this one because A is... No, you don't ignore it. You just have both answers. Good. Question number 10. Quadratic equation this has roots this. Without solving, it's the classic question. We do this every single one of these papers. I can't believe it was the latest question 10. But anyway, we're going to rearrange this to be W, what is it, W plus 1 all over 3. Just do the opposite of this. And then you put that in there. I imagine this is how most people have thought this. And you just, I mean, I times the whole thing by 81, which ended up timesing this one by 9 because of the 3 squared already there. I just didn't want to work with fractions. But anyway, this is just algebra. You just do it. You just get this, which is that. It's fine. And yeah, that's all good. So the roots of the cube equation, this are this, and this, determine this and this. Okay, so we know that the 3 roots must multiply to make minus this over this. They multiply to do that because there's 3 of them, so you have to shove a minus in there. And it's always this over this. So okay, that's fine. We know that the 3 roots, the 2, how do you usually describe it? When you multiply each of the 2 and add them all up, you get this over this. So that's what I'm saying. So this pair plus this pair plus this pair is that over that. And that's positive because they're in pairs, not in triples. And then, of course, if you just add them up, you get the one that's missing here, which is 0x squared. So if you just add them up, you get 0. You actually get minus 0 technically, or minus 0 over 4. But of course, that doesn't make any difference. So this is probably the easiest one to start with. We'll just get alpha in terms of beta, and then we'll just shove it in here, I guess, to solve for alpha. And that seems to make a lot of sense to me. That all turns into this. Sure. Is that right? That looks about right. And then you cube root, you get this. Okay, and then you solve for beta, which is this. And then to find n, so the values of the roots, I guess we should say first, are 3 over 2, I guess 3, and whatever alpha minus beta is, which is apparently that. And then we can shove those results into here to find the value of n, and times it by 4, of course, at the end. And you'll get this. And that's the whole paper. Thanks for watching, and I'll see you next time.